In this video, we'll be looking at prokaryotic DNA replication. And we're going to start with prokaryotic replication because it's somewhat simpler than eukaryotic replication, and we can use the fundamentals we learned here and apply it to eukaryotic systems. So we're going to start by talking about the enzyme that works on the lagging strand of E. coli, and that's DNA polymerase 1 or Pol1. Now, polymerases are what are called processive enzymes. A processive enzyme is an enzyme that does a lot of reactions without letting go of the substrate. And since the genome of an organism is huge and a polymerase is the enzyme that's adding a new nucleotide, it is good that our polymerases have processivity. It would be a waste of energy and take a long time if every time we added a nucleotide we would let go of a substrate, which is DNA. So our polymerases are what are called processive. Now Pol1 has two different exonuclease activities, has 3' to 5' and 5' to 3'. That means we can cut in either direction. It does not matter which way we are going. We can cut 3' to 5' or 5' to 3'. What this means is that we are very good at proofreading. Any nucleotide that is incorrectly incorporated, Pol1 can excise it from either direction. And with that means Pol1 has an error rate of one nucleotide in every 1 million to 100 million nucleotides. So it is very precise when adding new DNA nucleotides. Now, said Pol1 works on the lagging strand, and we said that on the lagging strand, when we're making Ozaki fragments, we need to have a RNA primer there. However, we don't want this primer in the final genome. So Pol1 is the enzyme that's going to be excising this primer for us. And it does so in what's called Nick translation. So between the DNA and the primer, we have a nick. We just have no phosphate there. And so what Pol1 is going to do is going to go and add new DNA while destroying the RNA. And this allows us to replace our primer with actual DNA. And our ligase is going to seal up the nick at the very end. Now, to understand how the polymerase works, we have to know what it looks like, and we're going to be looking at a Klenow fragment. And a Klenow fragment is found in most every polymerase that we know of. So for Pol1, the Klenow fragment has the polymerase activity, the 3' exonuclease activity, and the 5' to 3' exonuclease activity. And we can think of the Klenow fragment in two different domains. You have a small domain which has 5' to 3' activity, and a large domain which has your polymerase active site, and it has your 3' to 5' exonuclease activity. And the way to really think of a Klenow fragment is you take your right hand and you kind of make it into a claw, and your palm and your thumb, that's going to be interacting with the DNA. As you can see on this picture, this is where the DNA is, and that's where we're going to be adding new nucleotides around this palm region. Now, our cleft here is full of positively charged amino acid, which makes sense. Our DNA has phosphates, it's negatively charged, so if we're binding DNA, we want positively charged amino acids. And this type of active site is seen in just about every polymerase we've seen or we know of. So it is evolutionary conserved, so that must mean it is very good at doing its job of adding DNA to adding new nucleotides to DNA rather. So let's look at our active site. We're going to look at Klenow1, which is just another Klenow fragment from Pol1. And the active site actually allows Watson-Crick base pairing and really doesn't allow non-Watson-Crick base pairing. And This is a way to keep fidelity, or to make sure that the correct nucleotide is entered. Because if you try to mismatch nucleotides that, for example, A, T, G, C, if you don't have that, then you're not going to get the hydrogen bonds that you need to incorporate a new DNA. And so your nucleotide is not going to be incorporated without those hydrogen bonds. So this is how we actually do proofreading of incorporating new nucleotides. It's all based on hydrogen bonds. Are we getting the correct hydrogen bonds that are purine and pyrimidine bases? Now, what's interesting, at least to me, is that when we're near the active site of our Klenow fragment, the DNA gets warped. So normal DNA in your body has the B conformation. However, when it's in the polymerase, it kind of gets shrunk. It's kind of getting crushed down on itself to make this A conformation. And this conformation allows it to be more open, to allow for that DNA to be added in. And speaking of open, there are actually two different conformations of our Klenow fragment. So if you go back to holding your hand like a claw, you have an open conformation, and then if you make the claw, if you move your fingers and your thumb closer together, this is your closed conformation. So if we have the correct hydrogen bond structure when the nucleotides, so we have correct Watson and Crick base pair. That means we are forming hydrogen bonds to the purines and pyrimidine bases. This causes the claw to close, which will seal that new nucleotide, and it will incorporate it into our growing strand of DNA. So that's basically how the Klenow fragment works. Now let's look at the active site on an atom by atom basis. And usually the polymerase, no matter what polymerase you're going to look at, they work more or less the same. At your active site, you have two metal ions, and they're usually going to be magnesium plus 2 charges. And they're going to be surrounded by asparagine residues. So here, A and B are our metal ions. Right now, they're interacting with these asparagines. Ion B is also going to be interacting with the phosphates of our new nucleotides. Remember, our nucleotides are DNTPs. D for DNA, N means it's going to be one of your 4 bases, and it has 3 phosphates. And these 3 phosphates are going to be right next to another phosphate of the growing chain, and these aspartic acids as well. So we need a metal ion to help bring all this negative charge together. It's kind of bridging this negative charge. The A metal ion is going to be interacting with the A phosphate of our DNTP, and it's also going to interact with the 3' hydroxyl of our primer here. So remember, we're going to add this phosphate to this 3' hydroxyl. So this metal A is helping putting them in place and helping bringing this negative charge together. And metal B also helps orient this DNTP so that it is in the proper attack position. So these metals not only help to mitigate or shield the negative charge, they're helping to put the incoming DNTP in the primer in the proper orientation so that we can stick these together. And if we look at the 3' and 5' exonuclease, we'll see a similar mechanism with these metal ions. Now, E. coli has a lot of different polymerases, and they all have different functions. So polymerase 2, 4, and 5, they're really your repair enzymes for different types of DNA damages you might encounter. 2, 4, and 5 will help to repair those. Pol3, that's your main DNA replicase. That's what's going to be on the leading strand. And you have 3 different subunits there. You have your polymerase activity. You have your exonuclease, 3' to 5' only, though. And you have another subunit that we're not quite sure what it does yet. These three major subunits of poly3 will combine with 7 other proteins or subunits to make the poly3 hollow enzyme. So this huge complex is going to be adding DNA for us in E. coli. And like I said, we do not have 5' to 3' exonuclease, so we can't do Nick translation like we did in Pol1. We need that exonuclease activity to do our Nick translation. And that's it for this video. I will see you in the next video.